Thank you very much for being here. Today I'd like to talk to you about an effort that we haven't spoken about a lot, but which I think is really very important for the planning of our future exploration missions to other planets, and Mars in particular. So you've seen and heard, of course, and maybe even read or about pressurized rovers. Okay, so it's the idea that you get to a planet and you want to explore the place, but rather than just driving around in a spacesuit, which can only take you so far as the spacesuit will have life support supplies for you, you will be in a comfortable RV, a motorhome of sorts, and then you can roam around the planet and see things more leisurely. And if you need to go out for a spacewalk, you put on a spacesuit and then you go for a walk. So this whole idea of a pressurized rover actually has been around for quite a while, ever since I think it became realistic for humans to go into space and visit other planets. But in reality, most of the experience we have with these vehicles has either been strictly in the sort of a backyard field test type of level of experience, or simply paper studies. There has been very few practical studies that were done on a road trip, really off of a road, where you are simulating planetary exploration. So today I'd like to present to you some of the early results we've been getting, some of the early experiences we've had with this kind of work. So it can always come in handy. All the recommendations we have at the end will, you might find them useful if you get to plan a road trip on Mars. So roving off Earth. Well, so this is what we've done so far with people. This is the lunar rover. It was taken to the moon on the 3 last Apollo missions, Apollo 15, 16, and 17. It had seating for 2. In fact, they did not have separate rovers, not only because it was lighter to just carry 1 for 2 people, but there was concern that we wanted to keep the 2 astronauts exploring together, not have them, scatter and go off on their own. So this was what was taken to the moon. Because of the constraints of lunar missions on Apollo, you could not go very far with this thing. First of all, you could only go as far as your life support and your spacesuit would allow you to go. But on top of that, there was a strategy that had to be employed. You had to go to the farthest point of your excursion first, when your backpack was still full of its oxygen supplies, and then slowly make your way back, hitting scientific targets, because if your rover broke down on the way back, you would still have enough oxygen to walk back. And so as the mission went on, you were closer and closer to your home camp. That's a very restrictive constraint. On top of that, you still can't go very far, nor was it the intention. The Apollo missions were intended to do local investigations. But the idea of roaming farther afield is not new. Chesley Bonestell had beautiful paintings and science fiction book covers that showed a pressurized vessel in which you could go all-terraining on Mars. Science fiction stories like Lost in Space had this vehicle. It actually wasn't pressurized. You can see people sticking their heads out of these thin windows. But the idea is here you have a sort of a more comfortable vehicle to take you around. Of course, in sci-fi novels, movies, you see the pressurized rover. It's usually a sexy toy. So again, the idea is that you have a habitat that is now mobile. It's maybe a subset of your main base that might have more infrastructure, but you're taking essentially a somewhat comfortable life support system with you across a hostile planetary environment, and then you try to explore from it. It becomes your local base, okay, wherever you take it. So as far as real studies are concerned, here are some early studies from Northrop, mainly directed by Marshall Space Flight Center. So this is sort of the early rice cooker designed for your pressurized habitat. Grumman tried its hand too in the mid-60s. So all of this was in preparation for Apollo, of course, and beyond Apollo. There was the notion that we might stay on the moon and do other things, go farther afield. And so we came up with these concepts for long-distance roving vehicles. And in this particular example, you can see the idea of a habitat vehicle pulling a logistics cart. Okay, so in this logistics cart, you might have places to store rock samples, tools, additional life support supplies, etc. And then this concept, which I actually had a chance to see with my own eyes at Marshall Space Flight Center, was actually developed by GM. So this is a GM, MOLAB means mobile laboratory, okay. So GM developed this for Marshall, and Marshall then gave it to the USGS, and they used it in Arizona for a few years with 2 people at a time working out of it as a mobile geological lab. And the feedback was that this thing was way too unstable to really keep geologists comfortable. If you look at the profile there, the front end view of it, it looks really top heavy and not very wide based. Okay. But nevertheless, the idea was already there. In particular, windows looking downwards that would allow you to see the ground, and if only you had a means of going for a spacewalk, which this did not seem to have, you would be in good shape. Then we leap forward. During the George Bush Senior presidency days, there was a space exploration initiative. There was the notion that we would go back to the moon, onto Mars. And so NASA Administrator Truly commissioned a study called the NASA 90-day study to look at how we might go about going back to the moon and onto Mars. And so they came up with this rover concept. Again, it's the same idea. You are in a pressurized habitat roaming the moon. Notice that now you have robotic arms in the front of the vehicle to allow you to collect samples without having to go outside. And that, it turns out, I think is going to be a very promising way of going about this. This concept also wins the prize for the worst acronym ever. Okay. So there you have it. You want to explore Mars. It's a big piece of real estate. The land area on Mars is about equal to all the continents on Earth put together. If you get rid of the oceans, you wrap the continents into a smaller ball, you get Mars. There's a lot to see. My favorite spot, one of them, is Olympus Mons, this giant volcano. It's the tallest mountain in the solar system. It's about 27 kilometers high. The base of it, okay, is about 600 kilometers. So this gives you a sense of the scale here near the equator. Of course, at the poles, it's with this Mercator projection, it's blown up. But the point is, there are many sites of interest on Mars. You want to hit at least a few of them if you're going to be going all the way there. You need something to get you around. Could be a hopper, but then you're stuck with the problem of once you land somewhere, how do you get around? Okay, a hopper with ATVs or buggies, that gets complicated very quickly. Having a rover that just has the ability to do traverses is probably a simpler way to go down the road. So we've been actually leading some of the first deep field studies of the use of such vehicles. Now, I read a few comments online in response to the announcement of my talk that we're never going to send a Humvee to Mars. Why would we? You can't, run a combustion engine on Mars, okay, or diesel. Of course not. These comments are correct. This is not the idea. We don't plan to send a Humvee to Mars. We use a Humvee on Earth because it's a good all-terrain vehicle for where we work, and at the same time it can serve as a first-order approximation to what some of these rovers should look like, or at least be set up on the inside and how you might work out of them. So we have 2 rovers on our project up in the Arctic. The red one's called the Mars 1, the yellow one, the Moon 1, to keep everybody happy. But the yellow one actually got rebaptized and has the name O'Carrion. I'll tell you about this a bit later. So we've been going on with these studies since the year 2003, and these 2 Humvees are currently in the Arctic. NASA Johnson Space Center has been spearheading this great effort called the Space Exploration Vehicle since the year at least 2000, and it's a combination of the efforts, I think, of 2 people in particular, Rob Ambrose, who's a roboticist at NASA Johnson Space Center, and Mike Gernhardt, who's an astronaut, used to be with Oceaneering and is very interested in advancing, in creating mobility systems for the exploration of small bodies, but also planetary surfaces. So this setup came together. The chassis is actually deconnectable from the habitat itself. So you could imagine just roaming around on the chassis without the habitat. like you would the lunar rover we had on Apollo. Or if you put the pressurized habitat on the chassis, now you have a pressurized rover. The wheels can turn in such a way that you can do a complete 180 degrees on the spot, so you don't have to have even a turning radius. The turning radius is 0. At least it's the length of the vehicle, or half the length of the vehicle. And notice also the spacesuits at the back. We'll get back to that in a second. Another effort worth mentioning, the electric rover at the University of North Dakota. They have a good aerospace program there. So as you can tell, this is somewhat lower fidelity in terms of being able to go everywhere, but nevertheless it's a good vehicle for studying things like suitports, the fact that you can access your spacesuits through the back wall of the vehicle. So let's look at what experience do we have on Earth with planning these road trips. This is the yellow cruise. It dates back to 1931. It was sponsored by Citroën, okay, and Citroën sent a bunch of its vehicles on a long road trip from Istanbul to Peking. At the time it was called Peking, Beijing, and they went through the Gobi Desert, had great adventures, but of course none of this was documented in a way that we can really usefully use for planning a long road trip on Mars. Then we had, in the mid-50s, the Commonwealth Trans-Antarctic Expedition. So this was led by both Vivian Fuchs and Edmund Hillary, both famous explorers. And you can see that it took them several years to complete this expedition, but it allowed them by vehicle to cross the entire Antarctic continent on these tractor vehicles. Now again, very well documented expedition this time, but not necessarily in ways that allow us to learn specific lessons about how to plan a road trip on a planetary surface. My own experience with all this happened in 1988. My first experience with all this happened in 1988. I wintered over in Antarctica doing my national service for France at the time, and at the end of our winter over, we had a summer campaign on the ice cap. So we left the coastal station and rode in these vehicles about 100 kilometers inland to a point called D21. And this was, of course, an eye-opener for me because we were essentially roaming in a featureless landscape using just satellite information for our positioning and tracking. We had radios only, no video, anything to communicate with the rest of the world, HF radios. And other than that, it was just a really exciting experience. So the rovers were pulling, of course, sleds, and the sleds had supplies, fuel, food, and also drilling equipment, because the goal of the expedition was to go drill through the ice cap inland. So since then, we've been running this project up in the Canadian Arctic on Devon Island. And so Devon is the largest uninhabited island on Earth. When you go there, you are the population of Devon Island. It's about the size of West Virginia. You are beyond the Arctic Circle. When you're there, we go there every summer. And this is a project, the Haughton-Mars Project, that's led by the SETI Institute in partnership with the Mars Institute and NASA Ames. So we have an infrastructure in place. We have this base camp. That's a permanent camp, although it's not used year-round. It's only used in the summer. It's up year-round. What I should say is that to get there, you have to fly into Resolute Bay, and then from Resolute Bay, you charter a smaller plane and you go to Devon Island, and that's how you get to this place. On Devon, there's a gigantic, 20-kilometer wide meteorite impact crater that formed 21 million years ago. It's called Haughton Crater. Okay, so that's, of course, the prime attraction. We like this part of the Arctic because it's very dry. It's cold. Alaska is relatively wet. This is the dry Arctic, so it's a polar desert. Precipitation is less than about 13 millimeters per year. The landscape that it offers, the overall environment, is a step closer to Mars than anywhere else on this planet, really. Okay. I should say also that we use ATVs to get around. So these are these quad bikes, all-terrain quad bikes, which are turning out to be the best way to do local exploration. If you have to go, say, anywhere from 5 to maybe up to 7 kilometers from camp, ATVs are a very good and reliable way to go. So fact, we even do this occasionally in spacesuits. We are partnered with Hamilton Sundstrand, the maker and the primary contractor for NASA for life support systems and suits. With Hamilton Sundstrand, we've been looking at the design for future Mars suits together up on Devon every summer. And so every now and then they put some of us in their latest spacesuit, and we go about our business, which is field geology in this case, and provide feedback to the engineers on the design of their suit and its comfort, etc. So this has been going on now for over a decade. And you see here how one might use an ATV with a spacesuit to get around, to zip around, I should say. Very convenient, but a short distance solution. And in fact, the idea is that for Mars, this would be a very good short distance solution. You hop onto an ATV, and it can do several things for you. It can, first of all, lighten your spacesuit. If it's carrying part of the oxygen supplies, for example, that you need for your suit, you don't have to carry such large tanks if you have your ATV handy with you at all times. So every time you sit on it, you can see there are connectors at the bottom of the backpack that allow you to snap in, and then you can recharge the oxygen tanks of your spacesuit and therefore carry a lighter suit. Remember, you're on Mars. Gravity is not like on the moon. It's quite a bit higher. It's 38% of what it is on the Earth. On the moon, it's 17% only, okay? So lightening the spacesuit is a real challenge. If you took the spacesuit that we have currently to Mars, it would have a felt weight of 125 pounds, okay? Way too heavy for you to use. On Earth, it weighs 300 pounds, of course, so that's ridiculous to use. On Mars, 125 pounds, you cannot do field work with it. On the moon, it weighs only 50 to 60 pounds on your back. So that's why the Apollo astronauts were able to get around. Had we had a larger moon, it would have been really difficult to make a spacesuit for it. Okay. This is neither here nor there, but the robot, the rover these ATVs should be robotic as well. They would have the ability to follow you. So you step off of it, you go explore, and it would follow you so that if you pick up rocks, you don't have to lug them back to your ATV. There's a partnership, if you will, that would be created between human and robot in this sense. But look, this is Devon Island, vast tracts to explore. Even for our terrestrial field work, forget about simulating going to Mars, just understanding this place which we're studying, the history of the impact, the effects on the landscape, the level of shock from the shock waves of the impact that the rocks have been subject to. Just to study this gigantic crater, we have to roam to great distances from camp. And by ATVs, you're very exposed to the elements. You don't have a lot of options in terms of shelter unless you carry tents, and then that takes time to erect, etc. So how about having a couple of trucks, or at least one truck to get you around, was sort of the origin of the idea. So here are the reasons why we wanted this larger truck. We want to be able to carry people and cargo around. We want to have an ambulance in case somebody gets injured. We'd like to have a vehicle where we could, lay them flat and bring them home safely and keep them away from the elements. We want it to be a mobile shelter, just to set up a temporary base somewhere. We want it to be a mobile lab, to be able to do field work, not just field work, but analyze the samples, maybe cut the rocks. Like if you wanted to spend a week somewhere at the edge of a canyon, be able to analyze the rocks there, do some of the rock cutting, thin sectioning, or analysis of your samples on site. Okay. We also wanted to have it as a mobile platform, just to carry a sensor perhaps, or a robotic arm. You'll see we have some of those uses. And finally, of course, use it as a simulator for pressurized rovers to learn some lessons for Mars. So here's the idea. This is the simple Apollo scenario at its core. Step one, you reach a target region you're interested in with your lunar lander. Step two, you have a little rover that allows you to get to an area of greater interest. Step three, you step off of your rover and you walk up to the outcrop, you chip away and you collect your sample. So this is the stepwise approach to your scientific target, which in this case is the big boulder. In a grander scenario where you have a base on a planet or on the moon, you would use a pressurized rover to access a local area that you want to study in more detail. You would take a couple of ATVs with you. They would be robotic ATVs. They could serve as scouts for you. You would then hop onto one of these ATVs, drive up and explore locally your area of interest. This particular location could be tens of miles away from your base. This now allows you to do the local exploration at the scale of a few kilometers. And then step 4, you find something interesting, you park your ATV, you walk up, and you chip away at the rock. Right. So the pressurized rover comes into this scenario, this particular science and exploration scenario, in this way. It's giving you access to greater distances, sort of regional coverage around your landing site. Your landing site, you should probably realize, is likely to be relatively boring and safe. I mean, that's how landing sites are usually chosen. You want an infrastructure there. You're going to want to have good comms visibility, so no mountains around, no canyon walls, so landing sites, bases are usually built in relatively boring places. Look at McMurdo, etc. But what you want are mobility systems that give you access to sites of interest. So we approached different car manufacturers, but the one we were most interested in was AM General, because they made the Humvee, and we figured, this is Humvee territory. We need something that's really all-terrain, and by the way, can offer an option that has a cab so that we can live inside. And sure enough, they said yes. Okay, so they gave us this red Humvee, and this is ancient history for now. We took it up to Resolute Bay thanks to the Marines. We had a first expedition where the goal was to, once it was dropped off in Resolute Bay, to wait for the winter to come around, and then we would drive it overland across Cornwallis Island to Reed Bay. So you see pictures of this journey. And then from Reed Bay, we would do the 20-mile crossing. See, this is about 10 miles, to Cape McBain, right? So we put tracks on the Humvee. We learned the hard way that you cannot drive on wheels on thick snow. We had a crew that was minimal, just yours truly with John Scott, who's very well known for having led over 30 years of expeditioning in Antarctica, collecting meteorites for the U.S. Antarctic program. Okay, so the vast collection of Antarctic meteorites we have been collected largely thanks to the field guiding and expertise of John. And then Paul Amoralik and Joe Amoralik are both field guides and highly respected members of their communities in Resolute Bay. Paul was deputy mayor of Resolute Bay for a few years, and Joe is his younger brother. And so this was the team that was going to make this happen. Paul and Joe would be scouting for us on snowmobiles, and John and I were going to be in the red Humvee. So we left Resolute, drove across Cornwallis Island, got to the coast by 4 a.m. We left in the evening. The sun doesn't set.
How fast does that go?
This can go up to 60 miles an hour, but in this particular instance, we're not driving it more than 25 miles per hour. And of course, when we simulate road trips on Mars or the Moon, we limit ourselves to 5. Sometimes we allow ourselves to go to 10, but that's it.
We wait and have questions at the end, please.
Thanks. So the next day, we took off the doors, put on our flotation suits because we were going to cross frozen sea, drove across. It took 3.5 hours. We ran into hummocky ice, but we were able to look over the hummocks and found our way through and made it to Devon Island. This, by the way, emphasizes the value of the concept that's being proposed by JPL. They're proposing to fly a helicopter drone on the upcoming Mars 2020 mission. I think it's a great idea. It would do exactly this, which is to get some height, scout around for the rover to see beyond the hill. Okay, we didn't have a drone, so we just climb on the hood of the truck. Okay. But that's it. We just crossed the little barrier of ice that you can see there in the background, made it onto Devon. If you look back in the distance, that's Cornwallis Island over there in the distance. So that's what 20 miles looks like. And it was really painless. And I emphasize this because this is what led us to take the next step, which was quite a bit bolder and turned out to be a lot harder. Okay. So we parked the Humvee ostentatiously at the top of a butte. There was a ramp on the backside you can't see, but we even had time to do a parting shot a la Robert Falcon Scott. Okay, and then in the summer we came back. Thankfully, found the Humvee on top of the hill. You don't see it there, but this is Cape McBain, and that's our little Humvee on top of the ridge here. Okay. Okay, so we jumped onto it. We connected ATVs to it. So this was the idea. We're all inside. We drive around. The ATVs are used as robotic scouts or human-driven scouts when needed, but otherwise they're just in tow. Of course, in reality, they would just follow the vehicle robotically and not need to be towed. When we needed some scouting, how are you going to cross this big river? Of course, on Mars, it could be just a canyon, but here it was a river for us. We sent out the scouts, and they go check things out. We crossed the river. We got sometimes really muddy. When the rocks started looking weird, we knew we were closing in on camp. The geology near our crater is very, very interesting. All the rocks are beaten up by the impact. So now you're driving through impact ejecta blanket. So it's essentially very rubbleized. And then we made it to camp. Note the SETI Institute banner on the walls of our mess tent. Okay. So this whole trip was essentially pain-free, almost worry-free, compared to what's going to follow next. So these were sort of the good times. And in the following years, we just used this one Humvee for a number of expeditions on soft, smooth ground, over more rocky terrain, sometimes too rocky. This is a scree slope where at first the front track got completely out of whack, and then eventually by the time we got to the bottom of the scree slope, you can see the rear track hit a rock and flipped completely. So that was the end of us using tracks for overland traverses. They were really meant for the snow. They are okay for smooth terrain, but otherwise you want tires if you can for just day-to-day roaming around. So we would use the Humvee to service a remote camp that we had. This little dome there was a group of our teammates who were set up there for 3 weeks. They were doing drilling, and so supplies were brought to them back and forth between our main camp and this drilling site with the Humvee. So it has a very utilitarian role at times. We're not always simulating some pressurized rover traverse on Devon. It made it to the coast. It sometimes is used as a platform. So this is NASA Ames's K-10 rover, okay? And below the K-10 you have the K-9. Okay. We also have here an experiment that entailed the connecting of a ground-penetrating radar far in front of the vehicle so that it would not be disturbed too much by the electromagnetic radiation from the engine. But this was a way for us to probe the depth of the permafrost, the frozen ground, the ground ice in the permafrost underneath us. At the back, you notice that there is a spacesuit. So let's look at this whole concept a little more. NASA has been examining this very interesting and I think clever concept of having spacesuits that are left outside at all times. Okay. The reason why you want to do this is because one of the killers you're going to face on the moon and Mars is the dust. We learned that from Apollo. The suits get coated with dust from just any single EVA. The dust, of course, does bad things to the suit, but it also contaminates the cabin. And on Mars, it's expected that the dust would be very fine-grained and possibly toxic. It's replete with peroxides, perchlorates. So you want to keep the dust. Dust is the enemy on Mars. Exploring Mars is managing dust. You want to keep the dust outside. So this solution is ideal because you access the spacesuit through the backpack. The backpack opens like a refrigerator door. It has a double door. Okay. The outside door, so to speak, actually stays with the rover so that once you are gone on a spacewalk, you can seal the back of the rover still. But the other door that fits inside this door is the back wall of your backpack. Okay. And so You open these double doors, you climb into your spacesuit, and then you unlatch, off you go. So you can do an EVA very quickly. You mess around, you get covered in dust, you come back, you back into your cubby hole, you reconnect, and then you climb back out of your spacesuit backwards, out straight into the cabin again. So the dust stays outside with the suit. It does not contaminate the cabin. Okay. This is Rex Walheim. I actually was lucky enough to be the pilot scientist of the first field test of the Space Exploration Rover when it was tested in Arizona in 2008. Rex was my commander, so I'm helping him here. Well, I'm just taking a picture, but he's climbing into the spacesuit by, you see, he's opened the double doors. So this door here is part of the spacesuit. It will be the back wall of his backpack, and then this here is the actual door that will seal the rover once he's gone. So he climbs into his suit. That's the helmet visor, and then off you go. All right. Now, doing a pull-up like this is not that hard on Earth, but imagine on Mars, where gravity is only 38% of what it is on Earth. It's a piece of cake on the moon as well. So you don't have to be particularly athletic to have this mode of entry and exit, especially exit out of a suit. Exiting is sometimes hard, especially on Earth, because you've done a 2-hour EVA, you're really exhausted, and then now you still have to do a pull-up backwards to get out, so it can be awkward. So with Hamilton Sundstrand, we've been looking at how we might adapt our Mars suit with this suitport system, and so we've installed a suitport system here to the back of the Mars 1, and it's actually pretty good. So we do studies like, how long does it take? You're on a traverse, how long does it take for you to jump into your suit? Of course, you go through the procedures, you pretend you're pressurizing this, the suit is pressurized, but you pretend that you have to hook everything up, the radio, you have to close the doors behind you, you do the suit checks, leak checks, everything. So you go through the motions. There are procedures that are well timed and understood, but you also add the overhead that it takes to do this in the field, planning your EVA on the spot if it's improvised, how long does it take, going through the motions of deciding who will do what, who's going to lead the EVA, how many samples are we going to collect, what tools do we need. All of this has to be planned ahead of time so that you're not figuring out which tool you have to grab once you get out. So there's a planning that takes place inside. You go into your suit. That takes about 10 to 15 minutes once you're used to doing that. And then you go for your spacewalk. You come back, it takes about 10 minutes to reconnect and climb out. All right. Now, of course, every spacewalk comes with overhead, not just up front in the planning phase, but also afterwards. You got to rest, you got to debrief, you got to rehydrate. So a spacewalk in the end is pretty labor intensive and time intensive. And if Mission Control wants to stick its nose into the whole process as well, even though they are 20 light minutes away from Earth sometimes, it's going to be quite burdensome to do a spacewalk just to pick up one rock, for example, if you wanted to do just that. We call this contraption the polar bear feeder in the Arctic. Okay, so this is what the Mars suit might look like. Rear entry suit, gaiters to protect you from abrasion. You have a wrist iPhone, for lack of a better word. It, of course, gives you, you can use it as a checklist. You can also take selfies with it. All right, and then why is the suit blue? Because it's the color that contrasts the most. It's the complementary color to orange. Okay, so it's the most contrasting color on Mars if you want to see each other. And you also want it to be relatively dark to absorb more sunlight so that you can stay warm more easily. All right, but what we've realized with all these rover treks is that you don't always want to go out for a spacewalk. Sometimes you just want to examine a rock, so we do the drive-by geology. Sometimes you want to collect a rock sample, but it's really burdensome to have to go on some EVA to just pick up a rock, especially if you're not sure it's going to be interesting. We have explored further this idea that's portrayed here in this beautiful concept art by Walter Myers, which is how about doing a lot of your field science in IVA mode, not EVA, not extra-vehicular activity, but intra-vehicular activity. You do your science staying inside in the comfort of your rover, but you use robotic arms. Hey, and if you find something really interesting, well then now you can go out. But otherwise, if it's just a matter of picking up a rock to examine it, why not just use robotic arms? So we've equipped our Humvee with a robotic arm. We partnered with MDA Robotics for this. They built the robotic arms for curiosity and spirit and opportunity. And sure enough, we were able to have this beautiful arm pick up rocks in front of us with cameras. We could target the rocks we wanted. It would swing around, bring it up to the windshield. Of course, we might just have good cameras on Mars, but looking at a rock through the windshield is not bad either. And if you like it, you dump it in the basket. And if you don't, you just drop it and you move on. So now you are not wasting the resources for an EVA, not just the time, but the oxygen and the labor as well. It's very important to note, by the way, that 95% of the rocks that were picked up and brought back from Apollo were float. Okay, what that means is these are not rocks that were acquired by chipping away at an outcrop. They were loose pieces of rock found on the ground that turned out to be interesting or not, okay, that were picked up by the astronauts. So in a profound sense, what was done on Apollo and is likely to be done in many places where most of the rocks are found in the form of rubble like this on a regolith-covered planet, is that you'd be running into loose rocks all the time. So what you want is this ability to examine a rock quickly with a robotic arm and then drive on, as opposed to having to go on a spacewalk for everything interesting you might run into. Okay. Of course, the problem is that we've had trouble with the Humvee on tracks, on wheels. Devon Island can be muddy, and it's not so much that it rains that much there, it's the fact that the soil sometimes just retains a lot of moisture, and then when it gets warm enough in the summer, the ground ice melts, but it doesn't drain away. So you end up with these landscapes that look like they're completely dry at the surface because it's windy and wind dried at the very surface, but then you drive onto these rocks and then you sink. Okay, those of you who are familiar with Alaska will relate to this easily as well. So it became a fundamental problem in all our traverses, let alone on pressurized rover simulations, to get stuck, because if you're stuck on Mars like this and your rover loses its mobility, you are just watching yourself die. Okay, you're going to run out of oxygen. You're far away from a lot of things, presumably. So how do you get yourself out of trouble? Well, the solution, this is another illustration of us being bottomed out on what seemed to be a rocky landscape. Okay, but we actually, the vehicle's bottom is resting on the rocks right here. Okay, it's a horrible feeling. And it has happened on Mars with spirit and opportunity. Okay, so here they are trying to move ahead through the sand. So sand will be your number one enemy on Mars, aside from the dust, okay, when it comes to moving around, because it could trap you, and then if you are trapped in sand, then you are potentially dead. The solution is a second rover. Okay, the second rover. So we have boldly approached AM General a second time and said, hey, you know, your first rover was nice, but we're getting it stuck a lot, and you wouldn't want media to hear about this, would you? So I'm just kidding. But so could we have a second rover? And they said, sure. And so then we told them about our idea. By the way, we may not need to fly it all the way to Devon Island, which is very costly and logistically difficult. We could just truck it as far as north as we can, and then maybe fly it a little bit more to the edge of the Arctic Ocean. And then from there, we would just drive it on sea ice, because we've done that before. It was so easy with the red Humvee. We'll drive it all the way to Devon Island. In fact, we'll drive the Northwest Passage. Okay, so this is the Northwest Passage. We're looking at an older map of the Canadian Arctic, or North American Arctic. What I just outlined in red is the southern route, so to speak. It's the easiest way to go from the Atlantic Ocean to the Pacific Ocean through northern Alaska. And it's a southern route because it goes as far south as it can. Everything that's below the red line there is essentially the Canadian shield, the North American continent. North of the red line is islands. Okay. Now the Northwest Passage took a lot of time to find, and it was finally sailed by Amundsen in a very small boat called the JOA, G-J-O-A, in a remarkable expedition. But before him, many perished, many attempts failed, and it was really a widowmaker. And in fact, Franklin came in the news not too long ago because he and the entire two crews of his two ships, the Erebus and the Terror, 127 souls, disappeared basically in the 1840s looking for the Northwest Passage. And we never found the ships. We found the graves of some of their sailors. And then finally this summer, the Canadian government, as part of its attempt to also strengthen its sovereignty claims in the Arctic, had a big campaign to find Franklin's ship. And sure enough, they found it with sonar devices not far from where it was supposed to be, which is along the west coast of King George Island. So this is showing you the modern Arctic, if you will, in the summer, where you can still see ice, frozen sea filling some of the channels between the islands, the Northwest Passage, and then the star marks the location where Franklin's ship was found. And you can see that even in the summer, that's an area that can still have quite a bit of ice. So the poor guy and the 127 men were, probably had no chance of getting out of there at that point. So the ships were never found until the summer, but we found remains, human remains, all along King George Island down here. Okay, and not me, but of course archaeologists over time. And it was deduced that they might have gotten poisoned by lead. This was one of the first exploring expeditions that had the latest technology in food. This is a perfect example of why it's not good to fly something that has a low TRL, a technology readiness level. Canning was in its infancy. They were in a rush. Canning was the latest thing. Let's can all our food. They canned the food. The canning was done not properly. Lead was seeping into the food right from the get-go. By the time they got to North America from England, some of the crew started to get sick. They eventually, lead poisoning leads to dementia, and then of course you eventually die. So this is believed to be at least partly the cause of the demise of this expedition. They lost their ability to make good judgment in the Arctic. Okay. So for our Humvee, the second Humvee, this was the plan we presented to AM General. You're going to put together the Humvee here, just deliver it to us here at Ames in California. We'll drive it to Vancouver, truck it to Edmonton and Yellowknife, fly it to Kugluktuk, drive it on sea ice to Cambridge Bay. If we can, we'll drive the whole Northwest Passage. If we can't, we'll fly it on to Resolute Bay, and then we'll drive it to our camp. They said, sure. And by the way, we'd like it to be yellow so that when we take pictures of problems we have with it, we'll know which car we're dealing with, and you'll know as well. So they said, well, this is what we have for you. This is the vehicle they had. It had been in showbiz for 20 years. This slide is not projecting the way it's supposed to, but there's a long list here of movies it's been in. Air Force One, Dante's Peak. I mean, there's really a whole slew. Pretty much any film where there has been a Humvee of any sort, it's been in it. At the top here, it's actually a scene from The Rock. Sean Connery is escorted out of jail by Nicolas Cage in a black Humvee. That's our Humvee. There you go. They are inside the vehicle having a chat. That's our truck. Okay, so it got refurbished. Here it is, hanging high at AM General. Looks like somebody else wanted a yellow Humvee too. So it got delivered to NASA Ames on a flatbed. It got baptized here at the SETI Institute with Tom Pearson. This was the old the previous location that the SETI Institute had on Wisman Avenue. And then there we go. We're headed to Vancouver. Cross the Golden Gate, stop by some schools along the way, say hi, this is our truck. We're driving the Northwest Passage, good luck, Mount Shasta. Got to Vancouver, where we rejoined part of our team. So John and Jesse, we'll talk to you about them later. But Kira Lorber was our logistics manager. She did a fantastic job organizing this entire journey for us. Steve Bram is our chief field engineer. He was not with us in the field, but he took care of communications and our entire safety system. So that if we needed to call for help, we could just call Steve. From Vancouver, we trucked it to Edmonton and Yellowknife. So here are our 2 snowmobiles donated by Bombardier in Canada, arriving in Yellowknife with the Humvee. We put the tracks on. We drove into a First Air C-130 in Yellowknife, flew and landed in Kugluktuk, which used to be called Coppermine, at the edge of the Arctic Ocean on the western end of the Northwest Passage. We rolled out, and at this point we were poised to begin our journey from Kugluktuk to Cambridge Bay. So this is the crew. John Scott, you're familiar, never go on the ice without John. He's an incredible resource and asset. Jesse Weaver, who was only 18 years old at the time. He's a ace ATV rider and all manner of mechanic and technician for vehicles. He got special training at AM General, and so he was going to see the Arctic in winter for the first time in his life. Joe Maralik, you know him. He helped guide the red Humvee to Devon before. And then Mark Carroll was our cameraman. He actually was working for Jules Verne Adventures, our outreach partner, filming a documentary, and I'll talk to you more about this later. So anyway, we got ready. Each vehicle, in other words, the Humvee and the 2 snowmobiles, would pull a sled. The sleds weighed between 1,200 and 2,000 pounds. They were full of fuel, supplies, tools, spare parts, science equipment, batteries, you name it. The kids in town were intrigued, of course. And there you go, off we go. We called it also the Ocarian because the Ocarian were this race of yellow Martians that Edgar Riceborough wrote about in his stories. And they actually had an interesting story. They rebelled against the rest of Mars and just fled to the North Pole of Mars to hide at the pole. Okay, so we thought yellow pole, that all worked out pretty well. Anyway, this was the only map that we used. It was a navigational map. Hey, we were going to be at sea, plus there are no roads, so you just use a nautical chart. In fact, this was an aviation VFR navigation chart, because that actually had some useful infrastructural information. And then we also had a radar, satellite radar image of the Northwest Passage at the time. That was very important because on a radar image, what's bright is rough, what's dark is smooth. And so, first of all, the seaway was smoother than the rocky terrain all around. But also, within the darker regions, you can see that there was maybe you can't see it, but there's actually a strip of really dark stuff here, you see. And this is why we sort of hugged the coast. If you note the scale, we were still several kilometers off the coast most of the time, because that's 100 kilometers there. But we were essentially trying to follow a radar smooth surface all the way to Cambridge Bay. So there you go. We set off. The terrain looked really daunting, although not that different from what you might face just roaming around on the moon, for example. But the problem that we had was the snow. There was a lot of snow on the sea ice that was hard to predict far ahead of time, and it was really impeding our progress, especially given that we were pulling a 2,000-pound sled in the case of the Humvee. That turned out to be really difficult. Each track, I should add, weighs 400 pounds, so a lot of stress on the vehicle. We were progressing very slowly, and our gas consumption was horrific. It was 2 gallons per mile. Okay, sorry, 2 miles per gallon. 2 miles per gallon. Okay. Okay, so when we reached our first spot for an overnight on sea ice, we made the difficult decision that we needed to go back and get more fuel, because at this rate we were just going to run short if we tried to make it all the way to Cambridge Bay. So this was an important decision. We sent John and Joe by snowmobile back to Kugluktuk. It was fair game. We weren't violating any rules. It's like if we were leaving a moon base, we had more supplies there. We just went back to get more fuel, and they would haul it back, and we would continue. We didn't get help from anybody else other than that. So they came back with more fuel. We had to load the Humvee with fuel on the inside as well. Drove on, reached this beautiful spot, and then learned that the weather was going to close in on us very soon. So we started to prepare the snowmobiles for the windstorm, the blizzard. This might be a sandstorm on Mars. It's sort of the analog, so you might be stuck somewhere for days to 2 weeks. Sure enough, here's the blizzard. We ended up staying cooped up in this vehicle for 43 hours, okay, waiting for the storm to pass. That's close to 2 days, and of course you don't know at the 40th hour that it's ending in 3. So you sort of have to plan for the worst. Eventually the skies cleared. We drove on past the Jamieson Islands, beautiful basaltic flows. This wall of black is just lava flows upon lava flows. And then more bad news, we started seeing fog. If you see fog, it means there's open water out there somewhere, and that's not good if you are riding on sea ice. And then, of course, we couldn't see very well, and this was a crucial picture, because what happens next happens between this vehicle and Joe. Joe is scouting ahead on his snowmobile, pulling his sled. He went through a hump in the snow, nothing unusual. We are following his tracks so that we see how deep they are. And next thing you know, the Humvee stops, doesn't move anymore, and it's tilting backwards, and I see sky out my windshield. Okay. So this is what happened. We had hit a lead, in other words, a crack in the slab of the sea ice. It was covered by snow. Sort of your worst nightmare. I mean, it would be worse if the lead were wider, of course. The front track made it across fine, but not the rear track, and so we were essentially sinking through the back. We took everything out of the back. Everybody was safe, of course, and then we worked on a plan to get the Humvee out of its predicament. The tracks had no grip whatsoever on the snow or the water, and so what we did was to use the 2 most benign pieces of hardware you could imagine us taking along. We took 2 very sturdy steel bars with us just for that. If we didn't have them, there was no way we could have ever gotten the Humvee out of its predicament. Okay, but just 2 steel bars, which were taken along for this purpose. We anchored the steel bars by drilling into the ice and the snow. We had a hand drill. And with the winch that's on the vehicle, there's a front winch, we were able to pull the Humvee out of its situation. Okay, so this was saved by 2 steel bars, and there you go. These are that's essentially seawater that you're seeing pooling there at the bottom of this lead. All right. After this, I had to reassess. Okay, we were using too much fuel, not even close to what we had planned. We had planned quite conservatively, I thought, based on the experience of the red Humvees crossing. We had a factor of 3 more fuel than that. Well, it turns out we needed a factor of 4 to 5 more fuel with the loads we had and the snow conditions we were facing. We had an alternator that was giving up on us. We had this lead problem, which hadn't been a problem up to this point, but could potentially really lead us to lose the vehicle. And let's not forget the primary goal of this expedition, which was to get the Humvee to Devon. Okay, it wasn't to do science or I mean, there were scientific objectives as well, but they were not primary. The primary purpose of this whole trip was to go to get this thing to Devon. So we decided to just finish the trip. We could make it to Cambridge Bay, and at Cambridge Bay, I made some phone calls and got lucky. But before I go to that, here was a summary of our first trip. We essentially established a world record for the longest distance driven in a road vehicle on sea ice. Not that anybody cares, but it was 500 kilometers, 496 technically on the GPS, from Cambridge Bay to Kugluktuk. We were never on land, and that was done from here to there, which projected on the moon at the same scale would mean that it would be a drive from the crater Eratosthenes here along the Apennine Mountains on the moon all the way to the Apollo 15 landing site. Okay, gives you a sense of scale. So, you know, a nice traverse on the moon. This is an example of, summary of our log. Each one of these columns is a day, it's a 24-hour day. What's gray is when we're sleeping, all right? So it starts at 6 a.m., ends at 5 a.m. here. So we're sleeping when it's gray. The brown is when we are awake but not moving. The green is when we're moving. And the yellow is just preparation, so it's open-ended and can last much longer. Okay. So you can see that on a 5-day trip, on the 8-day trip we actually spent most of our time not moving. We were working out problems, trying to figure out. Here we were waiting for the weather to clear, of course. And then eventually when the going got good, we were driving a lot more. Okay. So the bulk of the distance was covered in the last 3 days. We returned some science. We sampled the thickness of the sea ice along the Northwest Passage over that entire journey frequently, and so we have a nice log of that. That's actually historically interesting because it's rarely done. You have to have, you know, the right equipment to do that, and the desire to be out there in the middle of the winter. So we have that. We also conducted a planetary protection study with Andy Scherger based at the University of Florida. So we collected samples of the snow, both up track and down track from the vehicle every time we parked it and stayed overnight. This was the food prep area. So we collected samples of dirt as well inside the Humvee, floor grit, but also of the snow behind the vehicle up front and upwind and downwind. So this is the direction of the wind, upwind, downwind. And the purpose was to see to what extent does, you know, a pressurized rover crew or something similar contaminate a pristine snow environment when it sort of enters it. Granted, this is the Earth, this is not Mars. The vehicle is not pressurized, so there's not a big differential in pressure between the inside of the vehicle and the outside. But nevertheless, there are strong winds. There are contaminants that we're not even trying to contain. You know, will we see a whopping signature of our presence in any one of these locations? And of course, we found lots of human-associated microbes on the inside of the vehicle and also behind it, somewhat, but otherwise nothing. No detectable signature of human presence otherwise. So we flew the vehicle from Cambridge Bay to Cornwallis Island, care of the Air National Guard from Minnesota. And then the next summer, we flew back to Resolute Bay, and actually next winter we flew back to Resolute Bay and drove it from Resolute to Devon, which the first time took 3 days with the red Humvee, and this time will take 13. Okay, and I'll spare you the details, but I'll just run through the expedition quickly. We had a whiteout. We, at some point, were driving towards the midnight sun, so we drove as much as we could, as fast as we could. And then we got to this the first red star here, where we had a first break. The Humvee was pulling a very heavy sled. The entire rear geared hub tore off at the back. So these, by the way, are jacks. They're inflatable jacks. You can inflate them with your exhaust. So that's a good way to jack things up on Mars. Here's the torn hub. So we got stuck here for 5 days. We had to call for the part to be shipped, to be flown to Resolute Bay. And of course, we sent somebody back to Resolute Bay, Joe, to get the part. 5 days later, he came back with it. We repaired the part. There you go. We even had to use a Coleman stove at the bottom there to, as a blowtorch to get the broken part off the vehicle. And then we drove on. We drove on until we got to this lake. We crossed this lake as fast as we could. Got to the beach, and now we're at the eastern coast of Cornwallis Island. The next day was going to be our attempt to do the crossing. This is what happened. We got stuck in snow again. All 4 tracks were touching seawater. There you go. But thankfully we had a rear winch and pulled ourselves out backwards. Then as we started crossing, we hit the 3rd star, which was this, a track flipped on a block of ice. So that broke the track completely. Thankfully we had 2 spare tracks, 1 left track and 1 right track. We used the right spare. Drove on, and then at the 4th star, just before we got to the coast of Devon, we sheared off the entire left track. Thankfully, we had a spare left track left. So we replaced the track, but we also sheared off the gear hub, and the gear hub we did not have any left. That was the one part that had been flown up several days ago from Resolute Bay. Now we needed another one for the other side. So getting it shipped up from the south was no longer an option. We were too far from Resolute to drive back. It would have been a bust. The expedition was coming to an end, and it was a disastrous end. We were losing the vehicle until we had this thought. What about trying to get to Devon with the snowmobiles, where we parked the red Humvee and scavenging the part that we need from the red Humvee? Okay, so John and Jesse took off a 3-day trip to Devon Island. They were the only souls on Devon. It was 50 kilometers away to camp. They got there, got the part. Meanwhile, I was staying back at the mothership, at the stranded mothership, with 2 cameramen. We added a cameraman. The director of the documentary came with us the second trip, and Joe was with us too. So here we were, just stranded. And Joe was on lookout for polar bears because there were polar bears. They were starting to get interested in our hot truck. And it looked like they were homing in on us. Okay, so, but they never got close, and then finally Jesse and John came back with the scavenged geared hub. Great success. John actually injured himself during that trip because he fell off a cliff with the snowmobile. They had a whiteout they couldn't see, and so he did a nosedive with the snowmobile that really bruised his leg. Anyway, we repaired the part, drove on, and then eventually crossed this circle of tracks so we now realized that we had been surrounded essentially by this polar bear who was walking in circles around our camp for several days. Okay. You see these tracks then? That's the polar bear making circles around our spot. And then finally, the final approaches to Devon were just horrific. How do you go through stuff like this? Well, thankfully, we had brought along 2 thick wood boards weighing 200 pounds each. We had never used them on any of the trips so far, and finally their hour came. And we had them for this purpose. So we started laying wood boards and drove on the wood boards from icicle to icicle to icicle, made it to the shore of Devon Island, and the vehicle was safe. So we left. When we flew over the sea ice, we could see our tracks. This is our 13-day trip, where you see the green where we were actually driving was very little. It was all waiting for parts, waiting for the weather to improve, getting things fixed, etc. Okay, very different expedition. And then finally, the 2 vehicles were mated at camp, so to speak. So what's in the future for us? And I'm going to wrap up quickly here because I think that we're over time. The thinking is that we'll have an infrastructure in a relatively safe place on Mars, but then you want mobility systems to go roam around. Vertical mobility to drill, to look for liquid water. Horizontal mobility to explore the surface of Mars. Your habitat might allow you to connect to your pressurized rover via a sort of a airport-style gate. And your pressurized rover, this is all from my children's book, could have this similar configuration to what we have inside the SEV at NASA Johnson Space Center or our Humvees. Bunk beds in the back, a cockpit in the front, a little galley area. The toilet is usually at the back behind a curtain in the middle aisle. And then you can see the suit ports on the back wall that allow you to climb into your spacesuits. The robotic arms up front with the little bubble for you to stick your head. And so information, of course, would be critical to having safe journeys. We didn't have updated radar during our trip. We didn't have a lot of means that would make such a journey much safer and more effective. It's a resource issue. I love this image because it shows the SEV in Arizona driving at night. And I like to sort of imagine human explorers on Mars roaming around, during the day in a pressurized rover. But then at night, mission control or the robot mode of the rover takes over. And so you're sleeping, but you're like in a night train. You're crossing this vast, expansive desert where there's nothing to see anyway. And then the next morning, you get to the edge of a canyon, and it's time for you to explore. So you can be mobile throughout the day or throughout the night and be very efficient at exploring. So here are some general lessons learned and tips you can use in other areas of life as well. First of all, a pressurized rover trip is an expedition within an expedition. It's not just you jump into a car, you go for your groceries. It's really something that has to be planned as an expedition in itself. The key to success is planning, and adapting. Okay, and I'll go over planning and then adapting right now. Planning, for your expedition to succeed, of course, you need resources and commitment. Resources helps the expedition happen when you have a reasonable plan A, good plan Bs, and a robust, unbreakable plan C if all hell breaks loose. Resources and commitment boil down to the people that you have on your team, not just the crew, but even the ground support team that you have. And then the commitment will result in a successful expedition if, in particular, you have a very clear goal. It's the same goal for everybody. Everybody is striving for the same thing. Adapting is this. Here's the reality. Exploration never goes as planned, nor should it. Okay? If you're really doing exploration, you're going into the unknown. If it's unknown, well, you can only plan so much. So it won't necessarily go as planned. One of the greatest difficulty that I've found doing these kinds of road trips is, well, I haven't found it to be too difficult in the end, but one of the challenges is indeed to accept reality. Okay, that you might not be making it, you might not finish your trip, you might not be able to carry out your whole expedition. Failure is always an option, unfortunately. It's not a desirable one, but it's always there in the trade space, and you have to accept it when you have to face reality. You have to also reassess and be ready to do that. So many expeditions have been lost, people died because they did not reassess. They somehow stuck to the goal, and eventually that leads to everybody's death. So you have to be reassessing realistically, quickly, and thoroughly. And then replan. And your replan might be to either try again or to not. Okay. Your plans, don't underestimate the importance of planning. A reasonable plan A means that it's a plan that's as independent of uncontrollable factors as possible. You need margins and contingencies. Margin means, for example, extra fuel to finish your trip. Contingency means places you could go get fuel if you actually ran out, but you could access them by your ATVs, for example, or your snowmobiles. A good plan B needs to be in place, in fact, several plan Bs, because plan A will break. Okay, and this is where you examine all the what-ifs of your plan A. Okay, some of these what-ifs will happen, and that's when a plan B will become handy. A robust plan C is because, the worst things can happen too, and you must be prepared to beat even bad luck. We took some chances because we were very tight on resources. We didn't have extra tracks, for example, for each side. We only had one extra track for each side, but not several. It's a risk, but so far we were lucky. We have to have a clear goal, and you cannot underestimate the importance of that, because the goal is what drives your expedition. In our case, we had to get the Humvee to Devon safely. It didn't matter if we didn't finish the Northwest Passage, or so that this actually helps your decision making. It guides your decision making. It also helps focus your planning. Okay, and it also secures your crew and your team's commitment by having a very clear goal when you set off for this. Finally, just a few words on crew selection. Don't underestimate, of course, the importance of a good crew and team. The criteria are knowledge. You have to have people who really are good at what they do. This is not the type of trip where you take necessarily your best friends or, your spouses or your parents. It's a trip where you want to have as few people as possible, but who are bringing in the biggest oomph possible in terms of their knowledge and their expertise and their ability to survive. They have to be healthy, physically and mentally, to the extent necessary. They have to be really motivated to do this. This is, the pictures are pretty perhaps, but it's actually quite physical. So you want to be really wanting this kind of experience. And incidentally, you don't know that it's going to succeed throughout. Throughout, as long as you're not on Devon, you could fail. And that actually surprises me every time, because you have this really sinking feeling that you might not make it. It's easy to tell a story afterwards because it worked, but while you're doing it, you're really going into the unknown. You don't know if it's going to work. You have to be adaptable, willing to see your plans change, and finally, you have to be altruistic. Think about others before yourself, your crewmates. So John saved the expedition several times. He's the one who said, hey, let's take these steel bars because we might need to pull the Humvee out of the ice. Jesse saved the expedition several times by, of course, fixing it. Nobody knew how to fix a geared hub, but he could. He had the training. Joe saved the expedition several times by finding the best way through the ice, to get us there. Mark Carroll saved the expedition because, in some sense, he was holding the camera. He was the eyes of the world on you all the time. You had to be on your best behavior and sort of make good decisions. So I credit him for that. And then Jean-Christophe, who was the director of the film, saved the expedition because even though he was very experienced himself in expeditioning, he stayed away from interfering with the decisions or the difficult calls, etc. I praise that as a quality because it's difficult sometimes to stay quiet when you might want to speak up and intervene. He was a good soldier, so to speak, on this trip, and that deserves a lot of credit. So they have produced a film that I've seen. It's about our expedition. It's based loosely on the journal notes that I wrote during the trip. It's narrated. My journal and voice are those of Zachary Quinto. Those of you who don't know Zachary, he's Spock version 2 in the new Star Trek franchise. And this is supposed to come out later this year in a theater near you, I hope. Okay. So we have lots of people to thank. U.S. government, Canadian government, Nunavut government, research partners, corporate sponsors, outreach partner. And if you have to leave, I'll understand, of course.
Was Mars ever alive? Is it alive?
We know now that in the early years of the 20th century, this world was being watched closely by intelligences greater than man.
As usual, when left to themselves, my thoughts turn to Mars and our search for life there. As we make our way deeper into the Arctic, the feeling of roving on Mars grows stronger. How far on Mars? How deep into the planet will our search for water and life take us?
So we could land this thing up there. Land it? Sure, but we're not going to get it back off.
How do you prepare humans for that kind of exploration?
We've begun inbound mass jet ascent.
You send them to the Arctic to get stranded while attempting to cross the Northwest Passage. It's all here in this journal. It chronicles our attempt to get one step closer to another world. A barren world frozen in time, wind-swept. Lifeless, or so it seems.
We have time, as we ran a little long, we've got time for a couple of questions. So keep your hands up and I'll get the mic around to you.
I hope that the mailing list will say when this is out so that we can all
Yeah.
see it.
Okay.
But thank you for the talk. I'm wondering what the chief, because Mars is a very different environment than the Arctic, and you know the dust is not snow, and there's radiation that you know you need a vehicle that would protect you from radiation. So what are the key differences in design and planning that you would, if you were you know dropping this thing on Mars or an analog to this thing, that you would do versus, you know, there aren't any Martian bears either. That's good. That's at least one positive.
Yeah. So there are 5 aspects of the Martian environment that are essentially lethal compared to even the extreme case on the Earth. The temperatures. So you have to have an environmental control vehicle that, because we can, even though it's cold outside, we can still survive the temperatures. On Mars, you could not, and so environmental control. Number 2, the pressure. So that's also an environmental control issue. Here we are under 1 atmospheric pressure. On Mars, you need a pressurized vehicle. So that in itself means that you have a pressure vessel that is your habitat for your vehicle. A pressure vessel out of which you want to go in and out of, so it has to have ports and therefore seals at these ports, and this is why the spacesuit suitport concept is both very attractive, but it's a source of risk as well, because now it's a potential breach in the pressurized vessel that you have. The third environmental thing is radiation. So you brought that up. Radiation, you're protected on Mars somewhat by your spacesuit, but not a lot. And in fact, you want to minimize your time in a spacesuit and maximize the time you spend in a proper shelter like a pressurized vehicle. But even a pressurized vehicle, it's unlikely to be lined by a lot of water or food, which are going to help absorb some radiation. So even a pressurized road trip will subject you to more radiation exposure than staying back at camp in a habitat that might have thicker walls lined with food and water. Okay, but we're not thinking of having lead walls, for example, on a pressurized rover. So you know you will be subject to some radiation. Now the good news from Curiosity is that if you're in an environment that at least does not have a lot of water in the ground or ice, then apparently the dosages that we're getting are relatively benign. They're not as bad as one might have thought. So Curiosity has a radiation dosimeter that's doing some measurements. But the radiation situation is expected to be much worse when you have hydrogen in the ground, in other words, ice, because then it's essentially helping cascade the radiation effect of the incoming cosmic rays, and you have more secondary radiation from the water and the hydrogen in the ground. So this is sort of ironic. You want to be in places where you can access water readily near the ground, presumably at higher latitudes, but then that's where radiation might be worse for you. Okay.
So what might be the role of cairns, pre-provisioned robotically or manually basis, or at least at the destination?
Yes,
and for
that's,
survival.
that's essential. That's one of the conclusions of our work so far, which is, and we even do it ourselves, even though it's not a life and death thing for us. We even do it ourselves. We pre-position fuel ahead of time. If we want to go on a long journey in that direction, say we want to go on a road trip, 50 miles out east, we would take ATVs ahead of time, position a drum of fuel, or drop it off by helicopter or whatever. It's the same idea. You would have a robotic scout do that for you. Just send it out there and beacon it so you can find it.
So what would the fuel source be on Mars? And also, considering that, like you said, dust is not snow, would there be a problem with the vehicle getting sandblasted, like in the windows frosting up?
Yeah, so sandblasting is not expected to be a major problem on Mars as soon as you're off the ground layer, essentially. And it's also in part because the atmosphere of Mars has such a low density. I mean, it's 100 times less dense than Earth's atmosphere, approximately. So the dynamic pressure and the ability of the atmosphere to carry a large dust grains is not good. I mean, the atmosphere can't do that. So it's only very fine dust that's carried, and that's not expected to do any damage to modern windows or glass. Mm-hmm. Yep. Fuel source. So certainly we're not using diesel on Mars, okay, and that's not the idea. We would use fuel cells, which are a very compact form of energy, rechargeable. So hydrogen, oxygen come together. Fuel cells would be the way to go, or rechargeable batteries, but somehow that have, really can carry good load.
How realistic is it to expect to not spread Earth germs on Mars? I know you're going to try to avoid that, but...
Yeah. So we've done one experiment on this. It's not a good statistic in the sense that it's just one experiment, but on the other hand, it's the only one we've made so far. You'd be hard-pressed to find anybody who's been in an environment that did that kind of study. So this is a starting point. But the starting point is that by applying the best techniques for detecting human-associated microbes in the lab from snow samples that were collected, when we could see them very clearly in the snow near the vehicle and inside the vehicle, as soon as we walk away from the vehicle some distance, like was shown there, we cannot detect them anymore. It doesn't mean they're not there, it means we cannot detect them. So in some sense, the forward contamination bit seems to be more limited than what one might have feared. But on top of that, the Martian surface itself is very sterilizing for Earth life. It has high UV fluxes. The UV flux on Mars is about 800 times what it is on the Earth. It's essentially a sterilizing environment. It's not just the UV, it's the radiation as well. So Earth-associated microbes are not expected to even have a good chance of surviving on Mars, even if they were implanted there, unless they were somehow buried, below a few centimeters. Yep.
So the internal pressure of a Mars rover, it's going to be the equivalent of suit pressures right now, which is about 1/3 a typical atmosphere then?
Yep, pure oxygen.
Okay, so...
But below the flame point.
Right, so then would the lander be also landing at pure oxygen at 1/3 ATM, or?
Presumably.
So they'll have to do the standard decompression and all that.
Yep.
Okay.
All right, well, thank you very much. Let's thank our speaker one more time. And it's, as is customary, we like to give a gift, so here's the SETI Talks cup.
Thank you.
And I was worried when I saw the numbers on the slide going by 195, 196. I thought, where are we going to end? But thank you very much. And those of you who'd like to talk with Pascal, he'll be here for a little while. Please come up. Thank you, Pascal.
Thank you. Thank you, David.